So thank you for having me today at the Edith meeting. I feel very privileged to be asked to talk. I'm speaking under the banner of paleoseismology, though I prefer to call myself an earthquake geologist usually. Most of my work deals with historic surface structures to understand permanent deformation, strong ground motions, earthquake recurrence, and seismic acid, which I'll go over today. And my paleoseismic experience in Australia involves exploring alternative methods for identifying active faults and dating recurrence intervals, which I'll also cover today. I like to start my talks by acknowledging the traditional custodians of the lands which are being discussed or where I have conducted the work. So that includes the Wurundjeri people of Melbourne, where I lived and worked doing my PhD on this topic, the Pinjinjara people and the APY people in the Central Deserts, where the Petermann earthquake surface structure occurred, and which you see in the background here, and a handful of other surface structures. The Noongar people and the Warramungu people from Tennant Creek in southwest WA, where a handful of other surface structures occurred, and the Mirrawong and Gadjurabang people of Kununurra and northern WA and NT, because I'll be talking about some field work I did there. I just want to acknowledge that sovereignty of those lands was never ceded by the traditional owners, and I think it's important that as geoscientists, because we study lands to which people have these really long cultural claims, and really strong connections, we should always work to improve the ways in which we respect those people and those lands. We might not always be perfect, but we can always work to be better. I'd also like to acknowledge my co-authors on this work, notably Mark Quigley and Dan Clark, who contributed a lot of time and ideas into this through the course of my PhD. Also, all of the other co-authors whose work I'm showing today, and collaborators and idea generators from conversations with lots of people. So I'm just going to start the talk by giving you a broad tectonic framework for where Australia sits and to get everybody up to speed on some terminology. Because we're talking about intraplate earthquakes today, I just wanted to point out what interplate would mean. In this context, this would be an earthquake that occurs on a plate boundary itself. So think the San Andreas Fault or the Southern Alpine Fault in New Zealand. Those would be interplate earthquakes. So therefore, intraplate represents everything else, which is why I dislike the term. If you only take one thing from this talk, I hope it'll be how poorly the term intraplate represents the complexity of tectonic regions. So for instance, the Christchurch earthquake is considered intraplate, and that places it in the same category as Australian earthquakes and of Central Asian earthquakes. And all of those places are distinct tectonic regimes and variable bedrock sort of contributions to faulting. So I just think that this term intraplate being applied to everything is kind of illogical. We have to subdivide that. So this term stable continental region goes some way into subdividing intraplate. It was defined in the 90s, and it's basically based on the age of a continental region. So the original definition sort of says these Archean cratons, associated Proterozoic terrains, Paleozoic fold belts, and Mesozoic or Cenozoic passive margins. So that covers about 2/3 of the global land surface. These dark areas are a rough guide of what's considered stable continental regions. I roughly georeferenced it from this Sholton-Mooney paper in 2005. Personally, I think this classification needs a rehaul as well. I don't think that these places are comparable either, but that's for another day. Just for now, just so that you know, stable continental region is this defined term based on age. So that's where Australia sits in global tectonics. It is an intraplate stable continental region. Now I'll give you some specific background on Australia itself. So a very general overview of Australian faulting. All the red lines in this map show you known or potentially active faults or folds. These are linear features that show cumulative offsets orientated to Australia's current stress field, and the current stress field has been in place for roughly 2 to 3 million years. So we call that the neotectonic period, and any fault that may be currently active within that stress field is called a neotectonic feature or fault. So these thin black lines model the directions of maximum compressive stress in the crust, or SHmax, or sigma 1. These are measured by borehole breakouts and Fokker mechanisms. So if you dig a borehole in the ground, the cylinder of that borehole might change direction, it might squish, and that tells you what the direction of sigma 1 is. Australia is quite unique in that its stress field is not aligned with plate motion. So in this figure here, you see Australia is moving forwards at 7 centimeters a year. It's racing along, but instead stresses in the crust are aligned with very far field compressional plate boundaries. So the Himalayan collisional zone, Indonesia, Papua New Guinea, and New Zealand, these are all imparting stresses through the Australian continent, which is why the direction of the stresses changes depending on where you are across the country. So earthquakes and active faults in Australia are generally reversed because it's this compressional stress field. We do get some strike slip earthquakes, but that's where faults are oblique to the stress field. And near tectonic faults are assumed to align with respect to this stress field. So you can see that most of them line up perpendicular to this because they're reverse faults. And again, that stress field was thought to be in place from about 2 to 3 million years ago. So that's our near tectonic period. The stress field is easily perturbed by mining and dams and things like that. So if you dig a huge hole in the ground to mine it out, or if you put a huge amount of water on the ground, you're locally changing the directions of sigma 1, which means that you might induce seismic activity, not very large earthquakes, but you do induce seismicity from that. The colours in the background in this map represent large-scale crustal differences, and these are important in Australia. Roughly, these tell us a bit about the bedrock. So in the east, we have Phanerozoic crust, which is relatively recent orogeny, sedimentary basins and magmatism. There's a bunch of volcanoes down here in Victoria. And so this looks something like the highlands in the Great Dividing Range. It has a much higher erosion rate. And in general, active faults in this region have higher cumulative offsets through time because they're outpacing this erosion rate. To the center and west of the continent is this pre-Cambrian non-extended crust. And so this is much older Archean cratons surrounded by Proterozoic orogenic belts and basins. And that part of the crust hasn't been doing much for a very, very long time. It has very low erosion rates compared to the east. And it looks something more like this very flat granitic desert. So the faults here have been colored based on Geoscience Australia's very rough estimate of slip rates. And I'm going to talk more about slip rates later. But you can see that the faults down here in the east in the younger crust have much higher estimated slip rates than those in the center and west. And partly that's because a lot of these faults haven't been explored. It's very remote and difficult to get out to these faults, but also they don't seem to have as much cumulative offset through time. They're not displacing geomorphic features at the same sorts of rates as we see in the east, where these faults are displacing rivers, they're offsetting young sediments, all sorts of things which you would traditionally expect of an active fault. I think it's important to note for international audiences that Australia experienced no significant glaciation through the ice ages. There weren't glaciers. So a lot of this landscape is very, very old. There's a reason I haven't talked about strain rates or GPS velocities. It's because we haven't had any measurable for Australia yet. There have been some GPS stations installed since the late 90s. They haven't measured any reliable velocities across the country. It's a rather complicated topic, so I'm just going to leave it there. But this is why I talk so much about the stress field, because we don't have a strain rate or a strain field or a velocity field to help us think about active faults. But the stresses, the directions of stresses do give us some understanding of what the orientation of faults might be, even if we can't tell where that strain is accumulating or if strain is accumulating. So this is what I'm going to be talking about today, surface rupturing earthquakes. So there have been 11 surface rupturing events in Australia in the last 50 years, which is quite remarkable. All of them were in the centre and west of the continent. And I just want to note that in some literature, you'll see this described as 9 surface rupturing events. It depends on how you treat the Tennant Creek events, which were in this location here. This map here shows those events. This was 3 magnitude 6 and above earthquakes in a 12-hour period. Each of them ruptured a separate fault, which is why I call these 3 surface rupturing events, but some people call them a single event. So all of these earthquakes occurred in the center and west, where there was no real pre-existing seismicity to suggest that we were going to have a magnitude 6 or above earthquake there. Not all of these were 6 and above. Some of them go down to 4.7, magnitude 4.7, so quite low magnitude events. If you look at these rupture maps of each event, which are scaled to each other, they show that these ruptures have quite complicated surface expressions. So if we imagine that a surface rupture is the surface expression of the fault, these demonstrate that there are relatively complex faults involved in this earthquake. Some of them are curved, some of them are very complex in different orientations, and some of them are relatively short. So that's what I did my PhD on, trying to understand why these surface expressions of the faulting are quite complex. This graph here shows the best estimate we have for hypercentral depths for these events. In some cases, it also shows fault widths in these blue squares. I don't particularly trust those fault width estimates. I think that they're very rough estimates, so I don't put much weight in them. But these black triangles show the hypercentral estimates, which are the best that we have for these earthquakes, and they're relatively trustworthy, though the seismometers were over 100 kilometers away in each event. These show that the initiation point of the earthquakes, these hypercentres, are all less than 8 kilometres, and most of them are about 5 kilometres or less depth. So these are very shallow earthquakes. And because they're very shallow, it means that these low magnitude earthquakes can rupture to the surface because more of the fault plane is likely to intersect with the surface. Before I get into the paleoseismology of these events, I just want to highlight an important point about basement controls. So this example is the magnitude 6 Petermann earthquake from 2016. It was in the central deserts of Australia. This top map shows the distribution of offset measurements along the rupture, and this middle map shows the magnetic anomaly map and the direction of crustal compressive stress, so the direction of SH max. For this event, we see a fairly linear rupture for about 20 kilometers end to end, and it has multiple peaks in offset, which taper off towards the end. The bedrock in this location is a heavily foliated granite, so you can see how there's foliation coming through here in this satellite imagery, and some blobs of granite, and this is the surface rupture coming through. So we see that bedrock is consistently, where we see bedrock at the surface rupture, it's consistently aligned with the same strike and dip as the surface rupture. For instance, in this example, this is the surface rupture running through here. And if we look at the geophysical anomalies, we see that pervasive bedrock fabric extends to depth, which also aligns with the surface rupture location and strike. So this fabric is perpendicular to the maximum compressive stress in this location, which means it's well aligned for pure reverse offset, which is what we see in all the focal mechanisms and at the surface. This is all just a very simple pure reverse event. The next example is the 1968 magnitude 6.6 Meckering rupture, which was 37 kilometers long end to end. It happened in farmland in Western Australia. The rupture is more complex. It has multiple overlapping primary scarps in a concave shape, and the along rupture net slip shows this maximum in the central region. And so that central region, if we look here again at the direction of SH max, this central region is aligned perpendicular to the orientation of that SH max, which means that it's really well aligned for reverse rupture, so it's no surprise that we see the maximum net slip in that location, because that's where most of the rupture could be accommodated. Unlike the Petermann example, where the bedrock structures were very linear, the bedrock in this location has been multiply deformed. It has variably orientated dike intrusions, which you can see in this map as black lines, and lots of foliation planes, as you can see in this map as well, fold axes, sedimentary structures, all sorts of things. We again see these at the surface and also in the geophysical anomalies. Similar to the Petermann example, we see that the surface structure overlies and aligns with these dominant fabrics in the bedrock. It's just that here these fabrics intersect at shallow angles to each other, so rupture is propagating along these variably orientated structures, which we're now going to call faults because they've ruptured, creating this concave surface rupture. So where bedrock structures intersect with rupture at a high angle, like at the southern end of the Meckering rupture here, we see that net slip doesn't taper off to a minimum. It actually stops quite abruptly rather than in the top here where it tapers off. And so we argue that rupture was propagating along these intersecting structures, reached this structure at high intersection, and that caused a structural complexity that halted rupture. So these two events represent end member models which encapsulate what we see in all of the 11 surface ruptures. In every case, we see that surface rupture aligns with the dominant bedrock fabrics, and the complexity of the rupture increases with the complexity of the bedrock, which is what we see between these two ruptures. So we argue that all of these earthquakes initiated on pre-existing fabrics, and that the orientation of the bedrock structures to the stress field was a primary control on the distribution of the net slip, as we see in the Meckering and the Petermann examples, and the length of the rupture. And what I mean by that is, in this Meckering example, if this rupture hadn't been halted by this poorly aligned structure, perhaps rupture would have continued, and that would have increased the length and the magnitudes of the earthquake. So all of this has recently been published by a paper by Habin Yang in GSA Bulletin, and it builds off a paper that I published in Geosciences, which reviews all available evidence for these surface ruptures. I just want to make a quick note that we also see that surface ruptures are being influenced by surface geology as well. So this is the expression of the surface rupture rather than the faults themselves. For example, in the Peterman example, rupture is very discontinuous at the surface when we map it at the surface. So you can see these red lines are very discontinuous, but in the inside, we know that the rupture isn't actually that discontinuous. It continues where we can't map it in the field. And the reason we can't map it in the field is that rupture is consistently cut off by dunes. So in these geological maps of some sections of the rupture, we see that rupture just stops at where the dunes start. We also see that where there's less bedrock at the surface, so in this example, the rupture seems far more structurally complex, but I would argue that that just relates to the surface geology rather than any tectonic factors. So surface geology is having quite a significant impact on how we can map this at the surface, but not necessarily on the faults themselves. So for all the surface rupturing events in Australia, we see no prior ruptures recorded in the trenches at all. So we see also not only no prior rupture in the trenches, but we see no offset sediments at the surface. We see no terraces, river terraces being offset. We see no drainages being offset through time. So there's just there's really no geomorphic or trench evidence of prior rupture on these faults, which makes it very difficult to estimate recurrence. Where we do have trenches, there's an absence of evidence in some cases in Holocene sediments that goes back to 10,000 years. In other cases like the Meckering, this shows unfaulted tertiary sediments. And in at least one example, in the Marriott Creek example, the trench showed unfaulted pre-Cambrian bedrock. In the Australian context, OSL dating maxes out at about 80 to 100,000 years. So we can date the sediments in these trenches and say they've been unfaulted up to maybe 100,000 years ago, but that's just a minimum because we don't actually know the true age of those sediments necessarily. So in the absence of datable recurrence, we've resorted to pretty alternative methods to estimate slip rates, namely using bedrock erosion rates. So all of the surface ruptures occurred in areas where granitic bedrock is at the surface or within a few meters of the surface. For instance, this is the 1968 Meckering rupture again. This is what the granite bedrock looked like, scarp rupture looked like in 1968 and again in 2018. And so we have this offset not only at the scarp, but also the hanging wall has been offset. All this granite on the hanging wall has been offset relative to the footwall. So we say that perhaps we can use granite erosion rate estimates from across Australia to estimate how long it would take to remove this granite scarp and also to make the hanging wall flat again with the footwall. So to give us an idea of what the minimum residency in the landscape might be. So for instance, we use these erosion rates of 0.3 to 5.7 meters per million years. That would mean it's going to take 6 to 3 million years to erode this scarp, which gives us an estimated slip rate of 0.2 to 3.2 meters per million years. There are many assumptions and issues with these slip rates, and I don't really like them, even though I was the one that put them in my paper. The main issue is that it produces anomalously high slip rates for really low slip events. So this graph here shows the historic surface ruptures and how much net slip was measured at the surface, and then the slip rate we estimate based on granite erosion rates. And faults with very, very low slip, so just tens of centimeters, could theoretically host many recurrent earthquakes and have them erode away in quite a short time, which means that they have quite anomalously high slip rates. But based on the observations of the landscapes and the seismicity and the faulting in these regions, I just don't think that is reasonable. So I think that these are overestimating the slip rate, but in the absence of any trenching or geomorphic recurrence data, these represent the best estimates we have for most of these faults. We recently published this paper where we tried to use erosion rates to estimate recurrence in a more comprehensive sort of study. Again, looking at the Peterman surface rupture from 2016, we see no evidence of faulting in the trenches, and we see no topographic evidence of the pre-existing scarp in this landscape. There's no geomorphic evidence, no offset drainages, nothing in the landscape to say that faulting had occurred prior to 2016. So if this fault had ruptured previously, evidence of that has been completely removed from the landscape since it ruptured. So we collected bedrock samples of granite from across the surface rupture region where the surface rupture is here. We collected all these samples very close to the rupture on these smaller bedrocks outcrops, and also at distance from the surface ruptures on very large outcrops. And the reason we did this is because we saw co-seismic damage to a lot of outcrops, particularly on the hanging wall where outcrops like this had been smashed apart. There were fractures, there were rocks displaced from them. In larger outcrops, there were boulders displaced and the tops of the outcrops had been smashed to pieces. We also measure 1 meter of distributed hanging wall offset relative to the footwall. So the hanging wall has been pushed up by at least a meter And so we argue that both of these things should increase the erosion rate of the hanging wall relative to the footwall, and also increase the near rupture erosion rate relative to the background erosion rate of the unaffected outcrops. We estimate that these higher erosion rates might persist in the landscape for up to 500,000 years before re-achieving equilibrium with the background erosion rates. So this graph here shows the samples relative to the distance from the surface structure and the erosion rates we measure. And you can see there's no systematic increase in erosion rate relative to the background erosion rates. There's no suggestion that bedrock closer to the surface structure is eroding faster, or that bedrock on the hanging wall is eroding faster. So if we're correct that erosion rates should retain prior shaking or offset in this region, or should show any prior offset or shaking, it suggests that these outcrops haven't experienced significant damage for perhaps 500,000 years. Again, there are lots of assumptions and issues with that data, but it's the best we have. But also this sampling that we did gave us very good erosion rate estimates for the rocks in this region. So finally, what we do is we use those erosion rates to estimate how long it would take to remove the bedrock scarp in this landscape. Not only the scarp at the surface here, we see lots of bedrock again at the surface structure, but also this distributed deformation that we see at distance. So the results suggest that it would take 500,000 to 1 million years to completely remove this scarp from the landscape, which pushes back any potential rupture to over 1 million years ago. So our best estimate suggests that recurrence is at a minimum greater than 1 million years. And personally, I think it's just more probable that this fault hasn't hosted a prior surface rupture, and that prior to 2016, this couldn't have been considered active. We don't have the evidence to definitively say that. All we can say is that recurrence is very, very long in this region, or non-existent. So all of the historic surface structures have no evidence of recurrence, but that's not the case for all the central and western faults. So there have been some fault studies where these arrows are pointing, where we see cumulative offsets, and there is datable material which can bracket the event and provide slip rate estimates. So we can get slip rates for some faults in this central and western part of the continent, in this pre-Cambrian crust, but it's just that the historically active ones seem to have slip, but no rate. They just don't have recurrence as far as we can tell. So studies in Eastern Australia by Dan Clark of Geoscience Australia and colleagues have identified and dated recurrence and cumulative slip on active faults in this sort of Phanerozoic crust. So for instance, this is the Lake George fault. It has 250 meters of offset, just a few kilometers from Australia's Parliament House. It shows a long-term slip rate of 0.1 millimeters per year, and clearly has geomorphic expression. This second example here is the Cadell fault, which runs across the New South Wales-Victoria border. It's offset the Murray River quite a few times, and it has a long-term slip rate of about 0.01 millimeters per year. But when Dan and colleagues look at these slip events in detail, it becomes clear that the long-term slip rates are really poor estimates of seismic hazard. Most of the slip, when we look at slip through time on this graph here for Lake George, most of the slip is being accumulated in very short active periods where the fault seems to be accumulating slip, but then it just seems to turn off and accumulate no slip for a very long time, turns on again, accumulates slip, and turns off. And this is not a sort of periodic pattern, it's very episodic. So these short-term active periods have much higher slip rates, an order of magnitude higher than the long-term averages, which means that slip rates are really difficult to define for a seismic hazard perspective. Generally, we assume that that recurrence on a fault is periodic, but in this case, in both cases, that assumption is false. We see this really episodic cumulative slip through time. So it's very hard to know whether we're in an active period or a non-active period on any of these faults, and that would change how much seismic hazard we would assume they could occur. So just to finish up this sort of section on how this relates to seismic hazard in Australia and some larger questions about tectonics. The emerging picture that we get from Australia from looking at the paleoseismology of historic surface structures and from paleoseismic surface structures is that some parts of the country, active fault maps just don't describe seismic hazard. So in the pre-Cambrian crust, we see some faults that just don't seem to have prior earthquakes, but some faults that do have cumulative slip. In the east of the country, we see this really episodic recurrence where we don't know if we're in an active or a non-active period at any one time. And so we have this non-homogeneous seismic potential across the continent, but it's also non-homogeneous through time. We also have a very short seismic record of earthquakes. The catalogue is only complete above 1980 for magnitude 3 and above. So that's just not long enough to understand the distribution of seismicity in a place like this. We also have seen that all of the large damaging earthquakes in Australia, these magnitude 6 and above earthquakes, have occurred in regions which we wouldn't have expected earthquakes. We couldn't have mapped an active fault there prior to them hosting a damaging earthquake. And we saw no evidence that they should have been there. So in terms of making a seismic hazard map, this raises a bunch of questions about how useful active fault databases and slip rates are in this particular tectonic environment. We also see from historic data that Precambrian Australia has higher length and slip to magnitude ratios when we look at scaling rate relationships. So this blue line shows global catalogue of earthquakes from Wells and Coppersmith, and the orange line is Australian events. And in these Australian events, they all have higher slips and lengths relative to their magnitudes. It's unclear what specific geological or tectonic factors play into this behaviour. It may be because these were very shallow earthquakes, like I said earlier. Maybe it's because of the bedrock controls, which I discussed earlier. I don't know why these events were so shallow. It might be because of stress differentials in this old Precambrian crust. It's also unclear whether we would see this sort of length and slip and magnitude relationship in Eastern Australia, where the crust is rather different. So that raises questions about whether we can apply this data across other stable continental regions, let alone globally. Clearly, these faults are doing different things to global databases. So the key points here are that in Australia, we can't assume that faults host recurrent earthquakes. We also can't assume that fault recurrence is episodic through time. These faults seem to be switching on and off, and it's unclear why they do that. So I think Australia is this really clear, extreme example of very odd recurrence behaviour. And I don't know that we can apply what we see here to places with high strain rates. Clearly, those are behaving within our general assumptions of how faults should behave in high strain rate regions. But I think that these examples show that we should be really careful about how we think of faults behaving in low and moderate strain regions. There's some potential that some of these things might be carried over in other places. And clearly active fault databases and slip rates are integral to seismic hazard assessments, but it's really unclear what to do in the absence of those things. If you don't have a slip rate, what do you do? If your active fault can't be mapped as active before it's damaging, what do you do? So perhaps we can map out bedrock orientations relative to stress fields, like I talked about earlier, and say that maybe some locations might have a higher seismic hazard. Maybe we can look at geological terrains and say some areas have high seismic hazard. We do also see that these historic surface structures seem to correlate with very large gravitational anomalies. These are big steps in the MOHO from pre-existing sort of Precambrian tectonic collisions. Perhaps those tectonic boundaries are concentrating strain in some way, and maybe they have a higher seismic hazard because of that. I really don't have any answers to this. It's an open question, but it does sort of raise questions about how we're going to map out seismic hazard without being able to map active faults. So these surface structures provide an unusual record of reverse earthquake surface offset and intensity observations, and I know that that's part of the Edith project, so I just want to touch on them very quickly. So in addition to a long rupture offsets, we also see distributed deformation in all of these events, or where we have good data, we see distributed deformation on the hanging wall particularly. So this example is again the Petermann earthquake. This is published from Ryan Gold. We have multiple forms of remote sensing offset estimates here. These are from Worldview satellite DMs, and this is from the INSAR. And we see in these cross sections across the rupture that we have a big step in displacement at the surface structure, but displacement is also distributed at quite a big distance away from the surface structure. So this is important for trying to quantify things like setback distances and engineering close to faults. Again, though, it's unclear how much of the Australian data can be applied globally because these faults seem to be quite unique in their settings. In the wake of the Petermann earthquake, we also mapped out observable environmental damage. So those are rockfalls, tree damage, cracking, all sorts of things, any damage to the environment. And we used the environmental seismic intensity scale to assign intensities to these. So this scale is designed for where you don't have built effects or infrastructure, or to compare those two intensity values. We see very strong shaking on the hanging wall because in a reverse fault, the hanging wall generally experiences much stronger shaking because of the dip of the fault. We also see intensity increasing towards the surface structure, which we could also probably expect. We've also done a bit of work on precarious rocks in Australia. We hoped to use them as paleoseismic indicators to narrow down regions that had experienced high PGAs in the past, with the idea that these precarious rocks should topple with certain PGAs, so the presence or absence of them could indicate paleoseismic shaking. But unfortunately, it seems like when we did erosion rate studies of some of these boulders, it seemed like the erosion was causing them to destabilize faster than earthquake recurrence, or our expected earthquake recurrence. So unfortunately, in this context, it just doesn't seem to be a useful technique. We also found a number of untoppled, very precarious rocks after the Petermann earthquake, which was kind of a nuisance. You can read a little bit more about these sort of fragile geological features in this paper by Mark Sterling from last year. So we can't do any work on precarious rocks, but what we do have for near-field strong ground motions is lots and lots of displaced objects, particularly in the Petermann earthquake. I documented over 1,400 displaced rocks in the near field of the earthquake. This shows the distribution. So they're along the rupture, but they're also all across the rupture. We see, again, much more of them on the hanging wall relative to the footwall. And these rocks are, when we compare them to finite fault models with near-field velocities, they seem to be recording directional and intense ground motions related to rupture propagation and directional seismic shaking. So this is rupture propagating along the fault and also seismic shaking coming out in a directional sort of sense. That finite fault modeling comparison also shows that this rupture was probably a bilateral rupture propagation. And so these rocks are basically behaving like millions of tiny seismometers all across the region. So quite useful indicators of near-field strong ground motions. And so I wanted to finish on something that I find really interesting, this idea that perhaps we need to take into account alternative sources of information for identifying paleoseismic activity, or alternative mechanisms for why earthquakes might be clustering through time. So this is from one of my favorite papers. These authors went into communities and documented oral accounts, or they looked at historical records of oral accounts of Indigenous people and related that to sea level change curves through the last 10,000 years. And they argue that a lot of these oral histories describe post-glacial sea level rise, but there are heaps of them that could equally describe earthquake shaking or tsunamis, particularly on the east and northern coast for the tsunamis. Here are just 3 examples. So for the Spencer Gulf, which is a fault-bound area of Australia down here near Adelaide, this is described as having been catastrophic rather than gradual sea level rise, where the sea broke through and came tumbling and rolling along the track, and the lagoons and marshes completely disappeared. Now, personally, I think that an earthquake is more catastrophic than gradual sea level rise. Again, in Port Phillip, which is right next to Melbourne, we know that there's an active fault bounding one edge of Port Phillip. This is described as a hurricane, trees bending to and fro, then the earth sank and the sea rushed in through the heads till the void places became broad and deep as they are today. Again, this sounds more like some sort of faulting or a shaking than gradual sea level rise. And in Rottnest Island over here near Perth, which also has quite a bit of active historic surface ruptures and seismicity, this describes the islands, which were once part of the mainland, as in some unaccountable way burned with such intensity that the ground split asunder with a great noise and the sea rushed in between, cutting off these islands from the mainland. Again, quite catastrophic rather than gradual sea level rise. So perhaps these histories, which go back thousands of years, potentially tens of thousands of years, could help us identify areas where prior offset has occurred to understand current behavior. Or additionally, like I said earlier, the stress field can be perturbed quite easily in Australia when we dig a dam or if we dig a big hole from mining. And so it also raised the questions of, during these interglacial periods where there was a lot more water or less water on the continental shelf, perhaps that might explain why these earthquakes are clustering through time on some faults. So as a final word, I just want to say that the locations and recurrence of faults is clearly very complicated in low strain regions, and a lot of our assumptions about fault recurrence and paleoseismology just fall down in these regions. The question I've been asking a lot recently is how much of this is applicable to moderate strain regions. So clearly in places like Central Asia, we have faults that are very active through time. They're clearly accumulating strain and releasing that seismically, but then there are hundreds of faults that just don't seem to be as active, and maybe they're behaving in a way that's more analogous to these low strain region faults. It's very hard to say, but I think it's worth exploring whether our assumptions about recurrence and slip rates and fault controls and seismic hazard need to be updated for these low and moderate strain regions. And I want to finish with this quote that I really like from David Denham from 1989. Consider the English migrants at Caddo in Western Australia who left California because of the earthquake risk, only to be involved with the rupturing of the stable Archean shield when their grocery store was severely damaged by the Caddo earthquake. If they'd looked at the evidence available now, they may well have stayed in California, where at least the whereabouts of most of the active faults are known. So thank you very much, and I look forward to the discussion.